In this video, we want to take a look at describing planes using parametric vector equations. Um, so the idea here is we're going to be given a point somewhere in Rn, and we're going to call that point x0. And I'm going to be given two vectors, let's draw it from here, u and v, that I want to be parallel to the plane. So x0 is going to be on the plane. So I got a point in space, and I've got two vectors, and those two vectors are going to be parallel to the plane. So, actually the vectors, of course, are based at the origin somewhere, and I'm moving them to be based at the point x0. So they look like they're in the plane, but they're actually parallel to the plane, because if they were drawn in standard position, they would be parallel to the plane. Now, in previous videos, we looked at describing planes given a point and a normal vector, and to produce a plane perpendicular to that vector. In the next section, we'll actually figure out how to take these two vectors that were given in this one, u and v, and turn them into a normal vector to then create that plane. But for now, we can do this without oh, and that's only going to work in R3, and what we're doing here will work in R anything. So given a point and these two vectors, it does determine a unique plane. It's the plane right there. And the question is, how do we describe it? Okay. So the thing is, we're going to describe it by saying any point on the plane will be able to be described in terms of starting at x0. So again, there's some coordinate system down here. So if you start with x0 and then you add some multiple of the vector u, maybe I'll need to come out to here, let's say, and then some other multiple of the vector, sorry, that was the vector v, and then plus some other multiple times the vector u, so a multiple of v plus a multiple of u, that was supposed to be parallel to u. Oh, this is ugly, but it is what it is. Then you can get to your point x. Right? That is achievable if x is on this plane that contains this point and is parallel to those two vectors. Now, our textbook, so the formula looks like that this point, x, y, z, or x1, x2 up to xn, this point is x0 plus a multiple of u plus some other multiple of v. So describing the plane parametrically, I have to have two parameters, s and t. Our textbook gives this as a theorem in R3 that planes can be described this way, and then in the next paragraph says, oh, here's a definition of how to do it in Rn. They don't call it a theorem in Rn, they call it a definition. It's like, assuming they know something about the geometry, they're saying, here's what we want the geometry to be. We want it to be the same. Okay, so here's an example. I want the plane through the point, this will be in R4, the point 1, 2, 3, 4. I want it parallel to the vector, the plane parallel to the vector this and the vector that. Okay, -3, 5, -1, 9, and 2, 0, 5, 1. So, according to the formula, what I have is the point that it goes through plus s times the first parallel vector plus t times the other parallel vector. This will describe a plane in R4. Now, I want to rewrite this. I mean, depending on what you're going to do with it, it always determines how you write things. And right now, I just want to illustrate a few points. So I'm going to multiply each of these vectors by those two scalars, and then I'm going to add the three vectors together to get this. And so I can see the parametric equations that x1 is equal to this first part, 1 minus 3s plus 2t, x2 looks like that, x3. Right, so I get these four parametric equations or one vector equation. They're describing exactly the same thing. Right? Of course, the vector equation here only has one equal sign, but it has four components. And in order for vectors to be equal, corresponding components on this side has to equal the corresponding components on that side. And so that's really 4 different equations. Now, I want to say that this looks, I'm hoping, familiar to things that we've done earlier in the course. In particular, if I choose to write my vectors rather than horizontally, if I write them vertically, and rather than using, pointy brackets, I use square brackets, this looks like a solution to a linear system, perhaps, that has some free variables. x1, x2, x3, x4, this column matrix is equal to 1, 2, 3, 4, that column matrix, plus s times this, plus t times that. And notice that the this and the that are the u and the v that we started with. These two vectors, only they're written vertically. This is, in fact, very much the case. That is, when we were describing systems of linear equations, when we were describing solution sets, and we had infinitely many, so we had a parameter or maybe 2 parameters or whatever, that we were describing things that looked like this. We were describing planes. If I had, this has got 4 variables here, 4 components to the vector, so we're working in R4, but I have 2 parameters, s and t. With those 2 parameters, I'm describing a plane. Now, the only time I wouldn't be describing a plane with 2 parameters is if u and v, this vector and that vector, are parallel to each other. So rather than taking linear combinations of 2 vectors like that, I'm taking two vectors like this, and I wouldn't be describing a whole plane. I'd just be moving out along that that line. But as long as these 2 things are not pointing in the same direction, then I am in fact describing a plane. Now, another setup where we might be able to describe a plane is if you're given 3 points. Right? If you have points A, B, and C somewhere out in Rn, then 3 points determine a plane. Right? That is, I can look at the vector from A to B. I can look at the vector from A to C. What just happened here? And those 2 vectors would be the vectors that are parallel to the plane that I can use as u and v. And let's take the point A as the point the plane goes through. Now, yeah, the plane goes through all 3 points, and I could use any one of them. But with the way I drew u and v, it's gonna look best if I use A as my point. So this vector here is c minus a, and the vector up there is b minus a. So using the same formula as we did above, I have that all the points on that plane can be described as a plus something times b minus a plus something else times c minus a. Now, this is a parametric vector equation describing the plane we want. But again, I want to rewrite it to show some other things. In particular, look at, let's see, I'm going to distribute the s and the t through. Then I'm going to take all the stuff with a's in it and write them out in front, and then factor the a out. And this looks very much like what we had in describing a line with 2 points, but now I'm describing a plane from 3 points. I can clearly see where the 3 points are, A, B, and C. B is multiplied by S, C is multiplied by T, and then A is multiplied by 1 minus both of those 2 things. So the sum of the 3 coefficients here is equal to 1. This was the same as we did for a line, except we only had 1 variable. We had t, and we had 1 minus t, right, for the multipliers out in front. What this is doing here, so this is A and B and C. If you look at the points where, let's say, s equals 0. Well, if s equals 0, this just turns into a 1 minus t, and this turns into a 0, and this turns into a plus t times c. Well, that is the line that goes through A and C. That's from the last video. So you're describing this line right here through A and C. That's when s equals 0. Likewise, if we did it with t equals 0, then this would be a 1 minus s times a. This would be an sb, and then plus 0 times C. And this would be the line that goes through A and B. So this was the line where, what was this? This was S equals 0. And now I've got the line through A and B, which is the line where T equals 0. And then, less obvious, but if you pick S and T to add up to 1, so like a half and a half, or 1 and 0, or anything where S plus T is 1, then 1 minus S minus T would be 0, and we would be looking at this line right here. Okay. And then you can talk about all kinds of points in the middle. For instance, this was S equals 0. If I wanted to look at S equals a half, it would be halfway up. It would be at the midpoint here and the midpoint there. This would be the line S equals a half. This right here, parallel to the other two that are already drawn, would be S equals 1. For instance, if you take 1, 0, 0, sorry, if you take 1 and 0 for S is 1, T is 0, then this one also turns out to be 0 because 1 minus 0 is 0. And that's just the point B. So this point is in fact on the line S equals 1. And likewise, there would be T equals 0, T equals a half would go right through here. T equals 1 would go right through there. And you can you can describe points in this plane by, this point right here would be the point where T equals a half and S equals 1. So you'd plug in T equals a half, S equals 1, figure out what that is, and figure the whole calculation out, and that's telling you that point X. Every point in the plane essentially has an S and T coordinate. I like this form right here because I can clearly see the A, B, and C and what I'm doing with them. Not as obvious here, although this matches what we did above, where the B minus A and the C minus A are the vectors parallel to the plane that I want. So there you go. There's the basics of generating parametric vector equations of planes in Rn.